Welcome back. Now you've had quite the eyeful in our studio, so just wanted to break it down and talk about interpreting our output. And so here was the output that we got initially when we ran our repeated measures ANOVA. And where we get the result would be this line where our within subjects factor, which was named time point, was analyzed. Now we noticed that when we ran the Moseley test though, that we had a very small p-value. And because the p-value is less than our alpha 0.05, we noticed that the sphericity assumption was not met. And so we need to keep looking down in our output to get more information. And so we read down where the epsilons were, and so we were presented with epsilons for Greenhouse Geyser and Hume-Feld corrections. And so looking at these, we noticed that the epsilons were less than 0.75, and so we want to use Greenhouse Geyser. And so when you get the Greenhouse Geyser epsilon, you want to correct your degrees of freedom. And so I gave you a code where you can calculate the corrected degrees of freedom for your numerator and denominator degrees of freedom. And here is the part of the code that you want to rename as needed based on what you called the object where your summary for your ANOVA analysis was saved. And then this last part of the code will give you the adjusted numerator and denominator degrees of freedom. And so we ran it and it looked like this. And so putting it all together, here is the main result from the repeated measures ANOVA table. But because our assumption of sphericity was not met, we want to replace both the degrees of freedom as well as the p-value, which you got right next to the epsilon for Greenhouse Geyser correction. And in putting things together, we've got the degrees of freedom here that got plugged into the parentheses, and then here's the F statistic, which is from the original table, and then the p-value read from right next to the Greenhouse Geyser epsilon, because we had to use Greenhouse Geyser correction. So translating that to APA style write-up, you're very familiar now with how to report the F statistic, and it's going to look very similar. And so I might say something along the lines of mean levels of belongingness to STEM significantly different across the measurement occasions. And then here's how we would report that F statistic. So italicize capital F and then immediately open parentheses and then the degrees of freedom, numerator and denominator degrees of freedom separated by a comma and a space. And then space equals space, the F statistic, comma, and then space, italicized lowercase p, and in this case, the p-value was less than 0.001, so we would just report it like this. And the degrees of freedom were adjusted for this analysis using the Greenhouse Geyser correction and then provided the epsilon. And so it's a good idea to explain that you made a correction and which correction you used if your sphericity assumption was not met. And so this is, a bit of an unusual case where the degrees of freedom is not in whole numbers, but we did make the correction and that's the reason why we have these strange numbers. Now that's all well and good, but you may be wondering in looking at these means, where are the significant mean differences? And so similar to, let's say, like one-way ANOVA, we need to know where the significant mean differences might be. And in order to do that, you want to run the post-hoc test. Now I'm going to show you one way to run your post-hoc comparisons. As you know, in R, there are numerous different ways to do the same thing. This one I think is one of the less complicated ones, but it's still pretty busy in terms of R code, so I would encourage you, if you need to run post-hocs, to just simply repurpose my code. Now, there are a few steps involved in running post-hoc comparisons this way. First one is to create the long format of the data. And so remember that we're working with wide form of data right now, where each level of our independent variable is represented by a column. And so we see that each time point is its own separate variable. The long format actually collapses that so that the time point is collapsed into one single variable. And so here's an example of what I mean. And so whereas we had 3 different variables before for pre, post, and follow-up, now that information is collapsed into one within subjects variable called time point. So you can see that for each person, they have 3 rows, pre, post, and follow-up with their corresponding belongingness score at pre, post, and follow-up. So here's one person, here's another person, and so on. And so this is a long format of data, and I'll show you how to do that using the tidyr package. And so you will need to install it and then load it before working on this. And so here's the code for step 1. And so you load the tidyr package, and then you will be saving your data set, whatever you name it. So here's however you name that long format of data. And we're going to use the pivot longer function. And then within parentheses, there's a lot of information, starting with what data frame you're using. So this is the name of your wide format data set that you already have in your environment, most likely. And then designate which columns to use for your dependent variable. And then names to would be where you name that within subjects variable. And then values to would be where the dependent variable should go, so the name of your dependent variable. This will probably make a little bit more sense when we see it in action in R. And then if you like, you can attach the new data, or otherwise just remember that you have to use a data frame, $, and then variable name in order to call information. So you can attach that new long format data if you like. And then go ahead and run a pairwise.t.test, where you're referring to your dependent variable, comma, independent variable, comma, and then paired equals true, then making a Bonferroni correction using the p.adjust.method equals Bonferroni to control for family-wise error. And so the more comparisons you run, the more likely you are to, just by chance, come up with a significant result. And so to control for that, you can use a correction method. And here I've inserted Bonferroni as the potential correction. It's a bit conservative, but it will do for now. And so let's meet over at RStudio and then take a look at how this works. All right, so welcome back to RStudio. When I think about the fact that this might be one of our last few times we're going to be in RStudio together, that kind of makes me a little weepy, but we're going to go strong and finish strong, right? All right, and so we have written down the post hoc comparisons code here for you. And so first of all, you will want to install, and you can go to packages and install if you would like, to install the tidyr package. I already have it installed, so I'm just going to load it for now. You can use the library function to load it. And then here is that long data code. And so here is what I called it, just long data, because, imagination is not very strong right now. Pivot longer is the function we're using, and then we've got all this information to put inside. And so here is my data set, which is in my environment. And then here is comma, and then columns equals. And so I'm telling R which columns should be included in my dependent variable. And so here you want to name the first variable that comes up and then the last variable that comes up in that range. And it's separated by a column to indicate that it is a range from belong stem pre to belong stem follow-up. And so basically this is saying include the columns that are belong stem pre, post, and follow-up within that range. And so you can also see that in the view as well, that include this, this, and this. And so with this column function, you're just indicating which columns should be collapsed into that long form dependent variable. And so here's the first one, and then here's the last one. And so you put the first and the last variables there. And then names to is basically what you would like to call that within subjects factor. There's no good elegant way to name this one, but I'm just going to call it time point. And then values to, and then I'm going to just call dependent variable belongingness. And I think that's simple enough. Okay, and so let's try running it. Okay, so now we've got long data. And you can also, if you're curious, you can do the view function and just have it pulled up so that you can check it out. And so remember, this is view with a capital V. And so here we have it. And you can ignore the first variables here, but you can see that the time point and the belongingness are now in the long format. Pretty cool. And so now we're in business. Now you can also attach long data. I don't remember if I have the other data set detached or attached, and so I'm going to try detaching Psych300 data to demo cleaned, clear the slate. And then I'm just going to attach long data, just so that I don't have to do the long data $sign kind of thing. Okay, and so now I've attached the long data, and this just saves me from having to type things like, long data, $sign kind of a thing. And so now we are at the point of running our Bonferroni corrected pairwise.t-test. And so here's the code, and I have the dependent variable belongingness, which is now in our long data set, and then time point, which is the within subjects factor, paired equals true, and then the adjustment method, which is Bonferroni. So let me run that. And here we have it. And so now we have made pairwise comparisons for our post-hoc test, so we can see where the significant differences are. And if you're curious about interpreting this and you don't like scientific notation, you can always do the scientific equals false and then run that, and it is a very, 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 very small p-value. And so we're going to hop on over now to PowerPoint. Thank you, RStudio. It's been nice working with you. Let's go back and talk about how to interpret this and how to write it up as desired. See you in PowerPoint. Okay, so let's take a look at our pairwise.t.test output. Now what you're looking at are actually p-values for those pairwise comparisons right here. And so when you look at these, you want to see which p-values are significant. And so here are the p-values with Bonferroni correction already applied. And if you have a p-value that's less than your alpha, in which case it includes the significant mean difference for that pair. And so when you look at this, where do you find p-values that are less than 0.05? You might have said over here, and you would be right. And so that would be the pairwise comparison between belong stem pre, so pre-test, and follow-up right here, as well as belong stem pre and post-test. And so pre-test and post-test are also different from one another, but not the other pairwise comparison. The post-test and the follow-up were not significantly different from each other, very large p-value. And so basically the pre-test differed significantly from both of the other time points. And so here is the APA style sample write-up now augmented with the report of the post-hoc test result. And so post-hoc comparisons using Bonferroni correction revealed a significant mean difference between scores of pre-test and both post-test and follow-up time points. And I've included the mean and the standard deviation for those time points just so that it's easier for the reader to interpret. But the most basic information is to point out where there were significant differences. And if you wanted to provide the reader with a little bit more information, you can add mean and standard deviation like I did, and that would be pretty good practice so that the reader can eyeball and figure out the magnitude of the differences, for example. Now you can get these group means and standard deviations either using the aggregate function, which you might remember from before. When you do that, if you have missing data, then you will need to add na.rm equals true within your function in order to get the information. Or alternatively, you could just go back to the wide form of your data set and then run your descriptive statistics on those three variables representing the pretest, post-test, and follow-up. And so you've got a couple of options for calculating these in case you want to add them in. All right, and so you have done a great job learning about repeated measures ANOVA and how to run it from start to finish. We've covered a lot of ground, and so let's do a quick summary. And so what repeated measures ANOVA does is to compare related means across multiple measurement occasions. And so the dependent variable is continuous and is measured multiple times. And then for independent variable, it is a within subjects factor that is categorical, and each level indicates a measurement occasion. By default, the analysis assumes sphericity, but if the assumption is not met, then you want to use either the Greenhouse-Geyser or the Hume-Falk correction for both the degrees of freedom and the p-value. And so we saw how to do that in R. And then if you get a significant ANOVA result for your independent variable, then go ahead and run your post-hoc test to figure out where the significant mean differences were. All right, so instead of your typical your turn exercise this week, it is your time to shine by testing your own hypothesis too. Woo! And so what you want to do is to write and test your hypothesis too. And so go ahead and follow the procedures that are demonstrated in lectures, and there will be a poster lecture as well, and so make sure to watch that. And if you need, please also run the post-hoc test, and so you will be running your repeated measures ANOVA from start to finish to get the results for your hypothesis too. Enjoy! And finally, have a fantastic week. Once again, great job this week. Congrats on getting to this point in the course. This is the very last lecture in terms of learning a new type of analysis. And so please pat yourself on the back and enjoy testing your hypothesis too. And I hope you have a great week or weekend whenever you're watching this. Take care, great job, and I'll talk to you soon. Bye for now.